I'm going to explain the brute force method that I wrote here. We have our two example cases here. Here's the take step method. It takes in the cost array, initializes I to -1, and the reason for that is we're starting before the array, before index 0. So we want to start over here in the cost array. We're initializing total to 0, and then we call on the take step helper method to calculate the minimum total cost of stepping through the cost array if we were to take one or two steps at a time. So here's the take step helper method. It takes in cost, I, and total. We have a base case here of if I is greater than or equal to the length of cost, return total. So if we step outside of the cost array, then we want to just return total. If I is greater than -1, total will equal total plus the value at index I. The reason for if I is greater than -1 is because -1 is not a valid index in the cost array, and so we don't want to get an error here. So we want to take either one step or two steps at each iteration of the cost array. So total will equal the minimum of what we return from taking one step versus what we return from taking two steps. Then we want to return the total. Explain the time complexity of the brute force method. We start at I equals -1 and total is 0. We take one step forward, I equals 0, t equals 10, and then we take another step forward, I equals 1, t equals 25, and t stands for total, by the way. Then we take another step forward, I equals 2, t equals 45. So the total of taking one step at a time through the cost array is 45. But if at the instead of taking one step at index 1, if we took two steps, I equals 3, that would mean that we're outside of the cost array, right? If the cost array were the first example provided, 10, 15, and then 25. Wait. Oh, sorry. I think the last number was 20. So if we took two steps to step out of the cost array, the total would be 25. Then we go up one, I equals 0. If at I equals 0 we didn't take one step, but instead we took two steps, I equals 2, the total would equal 30. And then if we go, so the total, the minimum cost of taking one step first is 25. So if at the beginning of the array, instead of taking one step, we took two steps, I equals 1, the total would be 15. And then if we took one step forward from I equals 1, the total would be 35. But if instead of taking one step forward at I equals 1, if we took two steps forward, the total would be 15. So at I equals 1, the total will be the minimum of 35 and 15, which is 15. And then at I equals -1, the minimum total would be 25, which is returned up here at I equals 0. It's 25 versus 15. So the total will be, the minimum cost, or the minimum total will be 15, right? And so that time complexity is 2 to the n. And the reason for that is because we calculate I equals 2, 1, 2, 3 times. We calculate I equals 3, 1, 2 times. I equals 1, 1, 1 times. So we're recalculating certain indexes multiple times. There is a way to improve the time complexity of the take step and take step helper methods. We can use dynamic programming. I created an object called memo, and I'm passing it from the take step method into the take step helper method. And for each recursive for every call of the take step helper method, I am seeing if that step is in memo, and if the total stored at memo I is less than the total that is currently being calculated. And I'll explain this in more detail on the whiteboard. When we take one step or two steps, we're throwing memo into that recursive call, and when we come back up, when we're getting the total of taking one step or two steps, we store the minimum total into memo I and then return total. So here is my whiteboard. So say hypothetically we had gone down the right branch first, right? So if we started out taking two steps, so we're at I equals 1, we get a total of 15, then we take one step, I equals 2, total equals 35, and then we return t equals 35, and then we take two steps to I equals 3. We step out of the cost array, right? So we return 0 from I equals 3. So the minimum total would be 15, right? Because 15 plus 0 equals 15. So now we would store memo 1 equals 15. And now if we were to go down the left branch, we calculate I equals 0, then I equals 1, and we assess. So what this is right here is cost 0 plus cost 1, that's 25, right? So the total is 25 here. And then looking at the code, we would be at if I in memo, right? So if memo 1 exists, which it does because we calculated it and assigned it over here, from over here in this step. So if memo 1, which is equal to 15, is less than the running total, which is 25, then just return memo I. And what that does is it allows us to skip the recursive calls down here. So we aren't calling we are not calling for take step helper I equals 2, and we're not taking two steps forward to I equals 3. We're skipping this down here and returning t equals 15. So that because we're not drilling all the way, because we're not having to drill down all the way, to the bottom, the time complexity would be T of n equals n. O of n. We used a recursive top-down approach, and we used dynamic programming.